Option. Right, so this is one, so it's gonna be.
Maybe it was only two.
Okay, thank you, and sorry for the trouble, but thank you, Jean, and the organizer, and I hope next year I will be there in person. This is, this paper just submitted 40 days ago, so it's recent, and as you see from the title, square difference factor. This is by Ayman Badawi and my co-author David Anderson and Jim Kokandol. Here is the definition. If you take a proper ideal mean I not equal R, because I know some define it as I not equal 0 and I not equal R. But here only means I not equal R. We call it square difference factor absorbing ideal, and SDF, this is abbreviation for square difference factor. If whenever you have the difference between square, you see a square minus b square in I, and here we need a and b not 0. Then a plus b in I or a minus b in I. One of the factor to be in I. Well, the first result, which is, not very difficult to prove, if you have a non-zero SDF absorbing ideal, then I has to be a radical ideal. And remember, radical ideal mean whenever you have x in in R and x to some power in I, then x is in the radical. So the radical of I is the set of all elements in the ring R, where for each x there exists an n, where x to the n is an I. Okay, the first question maybe comes to your mind, why a and b not 0? Okay, look at B, remark, and see B. Note that if A comma B is not needed when the ideal is non-zero. So if I is not the zero ideal, then you can remove the condition A comma B not equal 0. You only, A and B in R. You don't have this not equal 0 if I is not 0 ideal. But if you allow this, like if you go to Z4, the integers mod 4, then you can see that 0 is in fact a square difference factor absorbing ideal, but definitely 0 is not a radical ideal, because 2 square is 0, but 2 is not in I. Okay, so keep this in mind, that if your ideal is non-zero, you don't need this condition, A comma B not equal 0. Okay, well, this is like trivial result. If you have a radical ideal of a ring and the characteristic is 2, then I has to be a square difference factor absorbing ideal. Just observe that a square minus b square in I, it means a minus b, the whole thing square is in I. And since I is a radical ideal, then you're done. Okay, in this condition, as you see, we want A minus B in I or A plus B in I. So here is, this is like a result that we need to prove other result. What does it say? And this is crucial, by the way, in the proof of many of our results, this one here, this theorem. We want A minus B and A plus B to be in I. Whenever you have this condition, A squared minus B squared in I. Well, this will happen if 2 is an ideal in I. So A is equivalent to B, and definitely if 2 is in I, then the characteristic of the ring R mod I will be 2. There's no big deal. So if you want these two to be in I, A plus B and A minus B, then 2 has to be in I. Okay, that will make some of the work like, look at this result. If I is non-zero and 2 is a unit, meaning invertible element, then I has to be prime. So there is nothing new. So if 2 is a unit, then there is no difference between square difference factor absorbing ideals and prime ideals. They are equivalent. And here is a condition that you needed maybe to prove some of our result. This is like solving system of linear equation. What does it mean I to be a square difference absorbing ideal? This is equivalent to say that if A be in I, where A comma B, both of them are not in I, but they are in R, then this system of linear equation has non-zero solution in R. Okay? So this is like, and also to look at it, to observe that 1 imply 2, it was very useful in proving some of our results. Okay, the first thing come to your mind, can you give me a prime, square difference factor absorbing ideal in Z, in the integers, that is not a prime? I tell you yes. Here they are. Choose your favorite prime number, then multiply it with 2, then this ideal 2QZ definitely is going to be a square difference factor absorbing ideal. Where if you remove the 2 and you put another prime like a Q1 that is not 2, then it will not be it will not be a square difference factor absorbing ideal. Okay, these are, I think, natural things to look at. Like if you have an ideal I is an SDF absorbing ideal, and S is multiplicatively closed, and I intersection S is empty, what can we say about localizing I at S? Well, it's going to be the same. It's going to be IS will be SDF absorbing ideal. And then this is also natural things to do. What's going to happen under ring homomorphism? And non-zero here is crucial. In fact, in the next slide, we have example of a ring homomorphism where the zero will be SDF in T, but the inverse will not be SDF in R. So it's very crucial here, the non-zero. Okay, and this is expected, injective, then the inverse will be. And in C, if surjective and I is an SFD of R, and here we have to add one condition that contains the kernel, then f of I will be SDF. And also in C, by the way, the hypothesis that the kernel of F live inside I is crucial. And we have example. If you remove the condition kernel of F lives in I, then the result is not true. Okay, and here is the example. The first one is easy. You build this map in the natural way from Z to Z4. Well, I just told you 0 is going to be SDF in Z4. But if you take the inverse of 0, it will be 4Z. And I just told you the absorbing ideals in Z, the SDF absorbing ideals in Z, they have to look like 2 times a prime odd integer. Okay? And the same thing, here is another example where the kernel is needed in these things. Okay. Then von Neumann regular ring appear again. If every non-zero proper ideal of R is SDF absorbing ideal, then R mod the nil of R. Of course, you know what nil of R is the set of all nilpotent, is von Neumann regular. Well, if R mod the nil, it will be von Neumann. That means the dimension of R will be 0. If R is not reduced, then the nil of R is the unique minimal non-zero ideal of R. Okay. Here are some examples, but for the time, I like to give you more result. Like, okay, well, anyway, I'll go quickly on this one. Like all proper ideal of Z4 are SFD, all, because what are the proper ideal in Z4? 0 and 2. The ideal generated by 2 and the ideal generated by 0, which is 0. But not the 0 ideal Z20. If you take Z25, the non-zero proper ideal will be SDF, but not 0. Here, this is a von Neumann regular ring. This is all proper ideal are SDF. And if you take Z3 with Z3, the non-zero proper ideal of this ring, Z3 cross Z3, will be SDF absorbing ideal. And observe both of them are von Neumann. So it seems you cannot have a theorem, a general theorem that will take care of von Neumann regular ring. And even if you take R the product of 3, R is von Neumann here, product of 3 fields, and you take, this is a non-zero ideal, but in fact this non-zero ideal is not SDF-absorbing ideal. Okay, so here is what we did. We characterize rings with maximal ideal, like one. That's what we mean with the quasi-local. It's a commutative ring with exactly one maximal ideal. And this result, it tells you then every non-zero proper ideal is an SDF absorbing if and only if M is the unique prime ideal of R. And M has to be principal and M square has to be 0. Okay? So that's, well, so now you see clearly why Z4, uh, well, Z4 is exceptional on this because 0 is also like Z25, maybe what I meant, or Z9, because Z9 and Z25, they satisfy this condition. Okay. All right. Let R be a reduced commutative ring. Here we try to characterize in a way when von Neumann regular ring, when every proper ideal of a von Neumann regular ring will be SDF. Every non-zero is an SDF. It means if and only if R is a field or R is isomorphic to a product of two fields, F1, F2. Okay? And remember why this is related to von Neumann, because all of us know von Neumann regular ring, they are reduced. Okay? So if you have a reduced ring, every non-zero proper ideal if and only if this condition, and you have B, you can read it. What about if the characteristic of R equal 2, the characteristic? Then this is a clear case that then every proper ideal of R is an SDF. Maybe I forgot to tell you here, and here we have condition, by the way, on this previous result, that 2 has to be a unit. Okay, so we consider, in fact, 3 cases. 2 is a unit. The characteristic of R is 2. And then what's going to happen if 2 is not a unit, is a zero divisor? Okay, we have an answer for all the cases. So for in case of von Neumann, we have a complete answer to the question. Here, like if 2 is not 0, because if 2 equals 0, then the characteristic is 2, and it's a zero divisor, then the following are equivalent. Every proper ideal of R is SDF. Every non-zero proper ideal, exactly one maximal ideal of R has characteristic R mod M not equal to. Exactly one. So that means 2 is not an element of, it can be an element of exactly one maximal ideal. Exactly one maximal ideal of R has characteristic, oh, sorry, the opposite. What does it mean? That 2 has to be an element of every maximal ideal except one. Okay. Here is how to construct uh, uh, these SDF ideals. You take intersection of co-maximal prime, then I is an SDF absorbing ideal if and only if at most one of these PIs has characteristic not equal to 2. If and only if at most one of these, the characteristic of the ring R mod PI not equal to. Okay, we have a complete answer for a principal ideal domain. I will complete answer, but here observe if R is a principal ideal, A is trivial, I think. Well, it's not. If 2 is non-zero, non-unit, this is the interesting case, A. B is trivial. Then it will be I is an SDF absorbing if and only if I is a prime maximal ideal of R. I equal AR. And look at the A. A has to be prime, no big deal. Or I has to be AR, where A can be written as a product of irreducible, non-associative prime elements in R, and each one of them has to be a factor of 2. That's interesting case. So what I'm trying to tell you, if 2 is not a unit, does not mean 2R is SDF absorbing ideal. We A, you see AR, this A has to be a product of non-associative prime elements, and each one of them has to be a factor of 2. And here is the example. Take Zi. We know that R is a principal ideal. The number 2 can be written, 2 is not prime in this ring. These are the prime factors, I plus 1 times I plus 1. And you multiply it with minus I. Of course, I and minus I, they are unit in this ring, in Zi. Okay? So what are you're going to ask me, what are the what are the SDF absorbing ideals in this ring? This is how they should look like. 1 plus I P for some prime P in R not associative to 1 plus I. Okay? And of course, I'm assuming I is not a prime, because every prime ideal definitely is SDF. So the condition is if we're assuming the ideal is not a prime, then how they look like, this is how they look like. Okay, and we went, here is a very nice result. It tells you how to construct. If you take a proper ideal of commutative and assume I is the intersection of co-maximal distinct prime ideal, then Ix will be SDF absorbing ideal of Rx. If and only if I is SDF absorbing ideal of the ring. Okay? And here is another result, deals with the polynomial ring. Again, I think I run out of time.
Yeah, you have 1 more minute.
I'm gonna just give you one more and I stop. These two results here. Remember in the previous result, we have a restriction that P1 and Pn are co-maximal. Well, I can remove this condition and I let I to be the intersection of n prime ideal such that the intersection of any n minus 1 of the ideals P1 to Pn not equal to I. Then I is SDF if and only if at most one of the PIs has the characteristic where R mod PI not equal to. And this is a nice example. I mean, in my opinion, if you take the ring R with, polynomial ring with n variables, and you take a look at this ideal, I generated by 6, 2x1 up to 2xn, and then x1 product, x1, x2, x3 up to xn. This is an SDF-absorbing ideal. Okay, I think I have other result. Here are some of the references. And I thank you again, and I hope to see you next year in person. And thank you, Jean, and the organizer. Hello?
Any question? Can you speak up?
Hello?
I have a functional question. Can you hear me okay?
Can you hear us?
Yes, I hear you.
Functional question.